All right, well, good morning, good day, everyone, and this is Fred Schenkelberg, and welcome to today's Ascendo Reliability webinar. Um, this is a rescheduled one. A couple of weeks ago, we tried doing this event in our typical time slot, and a good number of people showed up. As again today, we got a good turnout, so I appreciate you sticking with me and coming back for this rescheduled one. I did spend quite a bit of time with Adobe Connect support folks to sort out all the ways I can set up and manage an unmuted line. There's always something to learn. I've been doing this now with the system for 3, 4 years, and the system keeps evolving, and I keep learning stuff. So hopefully it'll all work out. We had a little bit too much stress last week, and so we ended up bailing on the event. But happily, we're able to reschedule and give it a try again. So today I wanted to talk about stress strength analysis, just some of the basics of it, and really underline uh, how we as reliability professionals in general interact with or support this analysis, which is typically done. I think it's taught in common phrase use with mechanical engineers, but it's also used with many other types of engineering practices. The basic concept applies across all fields of engineering in the design work. And so we're going to talk about um, what it is, how we do it, and why it's important to reliability, and how we interact with this whole process. And so it should be pretty interesting. It starts though with stress, right? Our products work somewhere. Our systems operate in some environment. Now, some situations we take great pains to make a very benign, very low stress environment in order for some sensitive measurement system to detect, say, gravitational waves across the universe or something like that. So they're buried in a salt mine and very temperature controlled, everything that we can possibly manage and control, we do. Um, Most of our products are going to see the stresses that are around them, the weather, for example, uh, and also use. What kind of loads are they seeing? What kind of twists and turns and scuffs and marks and surfaces and temperatures and on and on and on and on. Our products don't see stresses like we do in the lab, where we apply just high temperature, and then we do a chemical test to see if the paint sticks on it, and then we do other things to it. Some of our testing will use combined stresses, yet we often are isolating those stresses in order to understand how they interact with our products. A customer's use of our products is not a test, it's the use of the product. And it's going to see this combined set of stresses and this accumulation of stresses over time that makes up the environment of where our product is going to be. And so part of our work is understanding what the day in the life of our product is going to be, from manufacturing and assembly and storage and shipping, installation and use and decommissioning. So how does it experience the world around it? And that's a part of what is very broad, right? Um, we'll narrow this down a bit, but stress is the starting point. We need to understand where we're going. The other part is the strength, right? Stress strength analysis, we need these two pieces. The strength is inherent in the product. It's material composition, it's manufacturing, it's free of defects or not. It's design by and large, but it's also a factor that, like stress, can change. And I should say that both of them are variable, and we'll get more into that in a bit. But the stress strength analysis is one of those things that has a nice clear name to it, and we're going to fundamentally compare the stress that a product is expected to see in the range and values and different kinds of stresses that are applied to the strength of products that we're putting out there. And this only really becomes a problem when the stress is larger than the strength and something fails. Now, products can fail for all kinds of reasons, and and not all. I'm going to hesitate that all failure mechanisms are related to a stress-strength relationship, and that we have too more stress than it's able to withstand. But I would hazard a guess that nearly everything is connected to this relationship in some form or fashion. I'm hesitating because I'm trying to think of software issues. If there's a software bug, um, it's just not going to work under a certain circumstance. But then again, there's a particular stress, a command or a demand or a timing or something that says, hey, we want you to turn this motor on, and software says, nope, I'm not going to do that. I'm a little hazy on whether that's related to stress strength calculations. I doubt it. Yeah. Yeah, good point, Mark. You can calculate this stuff. And we're going to talk about three different ways of going about doing this. But the concept is a key piece of what I want to get across today, and we'll talk about a couple different ways to go about doing the calculations. But before I get into this, let me ask you to hit the chat window. What are four ways that the stress strength distributions, I should say the distributions, so if I have a temperature distribution and I have a polymer melt point strength, for example, how can those two distributions change with time? Now, there's tons and tons and tons of failure mechanisms at play, but in general, how would the distributions change? Yeah, aging, wearing out, right? So what happens to the distribution if something's wearing out or aging? So wearing out would be the strength is deteriorating, right? So maybe the mean is shifting closer to where the stress levels are. So yeah, temperature change, it's a stress, right? Well, let's use Micah, let's use the fake news around global warming, right? Although this summer here in California has been remarkably chill. Um, but thermal cycling, we're getting more and more varied weather than we normally do. Ocean temperatures are certainly changing, but over time, it's not only that the environment around us is changing, which by and large has been rather subtle, but it's more extreme on both high and low ends. But we're also seeing that people use products in more stressful situations. The earliest cell phones were expensive and very fragile and were used very gingerly. Whereas people got more familiar with them, they got used in more and more places that had more stresses applied to them. Those are both parts and pieces to that. Right? Yeah, higher loads. Mark, exactly. Bridges that were built decades ago, 50, 60 years ago, are seeing loaded vehicles and more vehicles than they ever have, whether they were designed for it or not. Now, some bridges have plenty of margin in them between stress and strength and are maintained well so that they retain the strength that they were designed with, and so they work fine. It's when that um, the increasing amount of loads was not anticipated, and or the maintenance programs and inspection routines don't keep up with that. This can happen. There's great cases of that. So Raleigh, corrosion is a failure mechanism that would reflect, say, moisture and contaminants on, say, a metal or on a piece of material that then um, corrodes or eats away or deteriorates the material, right? So rust on a piece of metal, it actually changes the dimensions of the metal. And so that change in dimension um, deteriorates its strength. And so it can change the average value, but it can also change the variance. So stresses and strengths can spread out and become more wide, more a higher high and lower lows, but it also can shift left or right on the mean value also. So we'll keep that in mind as we go forward, because what I see most people doing whenever I explore how design teams are using stress strength analysis is they often don't include how it changes over time. They do a finite element model. They look at it as here's my stress, here's my strength. Okay, we got enough margin. But if you only use the mean values or worst case values, it doesn't include how it changes over time. And that's where reliability really comes to fore to keep that awareness pretty high. So let's dive a little bit more into stress. So measure it. Um, some of it's already measured for us. There's weather stations all over the world, most likely in places where your customers are or where your product is being used. Some places are a little more exotic to get to, a little less populated, but it's less likely that you'll have a lot of your products there. Usually our products are where people are. And where people are, there's lots of weather stations. So NOAA, N-O-A-A, has massive databases of reported weather station data that includes temperatures, min and maxes, trends, rate of change, humidity, or not humidity, they do water vapor or moisture in the air. Dew point, I think, is another term that's used. The rain, wind speed, pretty much any weather data that you can think of is out there. The good news is that by and large, indoor temperatures are, are generally sheltered, so they're a little more benign. But when I was back at HP, we had a whole bunch of instruments, inkjet printers actually, that were instrumented up and in homes, and we mapped the in-home temperatures and humidity and things like that to the reported weather station data. And they tracked remarkably well, and they were actually very close. They were much closer than we expected. Apparently, a lot of people leave their windows open. I don't think that's necessarily true in North Dakota in the winter or in Houston in the summer, yet it was a lot closer than we expected. So you don't get a lot of benefit by just saying, oh, it's in the house. Now, I also found that with the businesses, depending on the part of the world you're in particular, we had a bunch of corrosion on printers, and and part of the corrosion process was due to condensation. And we're like, these are office printers, they're in office buildings, and it wasn't until we recognized that office buildings in Korea, in Seoul, Korea, which has a lot of air pollution, uh, tended to turn off their HVAC systems on the weekends and sometimes even overnight, and would leave windows open to ventilate the building. And that would lead to the rapid changes of temperature, and dew would form on office electronics and everything else for that matter. But also, it had all the contaminants that were in the air. And so, oftentimes, what we see is the stresses in, say, a requirements document will have a min and a max. So it's got to go to minus 20 degrees Celsius to 40 degrees plus Celsius. That's our range. Well, that doesn't really tell us a whole lot of anything, right? And it might be worst case. It might not be. There are places that get hotter and there are places that get colder on occasion, but usually for a very brief time. What I recommend, especially for those stresses that are critical to your product's performance, is get the distribution. So temperature is the easy one. Go get the weather station data in the regions that you're expecting your product to be used. Get the histogram, get the distribution, get the data. And so I did this years ago for a client. They were putting in solar panels in California, and they had a couple of different sites. So we found weather data for those sites and got the distribution. And we were able to make decisions based on, say, the 90th percentile of high temperature, not just the worst that it ever got for a few minutes one afternoon on a particularly hot day, but closer to that edge, which was more likely to occur. In some cases, we used worst case, but other cases we used a percentile, and same for low temperatures. and other stresses like wind, for example. But having the distribution allowed us to balance the design decisions based on, well, what was the uh, probability of that risk occurring and for how often, how frequent. And so it gave the design team really clear information about so that they could make better design decisions. Now, the other thing we did is using these distributions, we also were able to look at how they're changing over time. As areas became more developed, some of the weather stations were rather illuminating, like airports are often based in a place that's remote initially, and then a community builds up around that. And if you're in an area that's relevant for your product, the current temperatures there may be pretty nice, but once you put a lot of asphalt and a lot of buildings and heat trap in there, the temperatures tend to go up, and you can monitor and measure those behaviors if that's important to you. Um, so we don't use the Farmer's Almanac and the grand averages, or don't use some international standard that gives you min and max. They rarely, if ever, give you the distribution. Just go get the real data. Now, when you have the opportunity, instrument your systems and go measure it yourself. Get your data in your application is even better. But for some systems, we can do that with the existing information that's out there. Yeah. Um, I'm looking at some of the comments here, temperature change, warehousing locations. Yeah, Dave, warehousing locations on the docks on a saltwater front or a wharf, um, not always the best place to have your products hanging.